Um, so let's begin with section 7. This section is on inverse functions, and I know you've been seeing inverse functions since your Algebra 1 days even, right? Um, so inverse relations, right, exist when one relation contains, let's say, the point B comma A, and the other relation contains A comma B, right? So it's when coordinates are switched. Take a look at some inverse relations here. In the first case, what I have here is y equals x squared minus 4, okay? And that's a parabola, right? So let me actually color code this. When you graph that parabola, it's this blue parabola, right? That's what you get. That's y equals x squared minus 4, all right? The inverse of that is x equals y squared minus 4, or y squared equals x plus 4. And that's this green sideways parabola, right? So now I've got an inverse and now I've got a relation and the inverse of that relation. I'm not calling any of these functions because the green one clearly is not a function. So we're just calling it a relation. So now there are two things that we have to take a look at. First of all, look at this red dotted line. This is the line y equals x, right? And one thing is, if you graph a relation and its inverse, the two of them are symmetric around that red line y equals x, which means if I were to take this blue function here, this blue graph, right? And imagine folding that diagonally along the red line, right? Look at what happens. If I fold this along the red line, look at what happens. Each of these points match with one of the points on the green. Do you see that? So that's sort of how it works. It's kind of hard to visualize, but like if this is the line around which I'm folding, or imagine like mirroring the blue over that, then look at what happens. Each point on the blue graph is mirrored on the green graph. So that's how a relation and its inverse are related. If you look at it just by coordinate points, look at how the coordinate points look. Take a look at the left side, the table on the left-hand side. I have a coordinate -3, 5. In the inverse, that corresponds to 5, -3. Another one, 0, -4 corresponds to -4, 0. So all the x's become y's and all the y's become x's. All right, so those are the two things that are important. Okay, so now, if the inverse relation of a function is also a function, then it is called the inverse function. So in this case, look at the green, that's the inverse, that's not a function. So I can't call it an inverse function, it's just the inverse of the first one. All right, now, another important thing then is not all functions have inverse functions, right? So this one here, clearly that blue does not have an inverse function. So how do we know if a graph will have an inverse function? Well, that's when the horizontal line test comes in. A horizontal line test says if you have a graph and if you draw a series of horizontal lines through a graph, and each horizontal line crosses the graph at only one point, then that function will have an inverse function. Okay, so this clearly does not pass the horizontal line test, so it does not have an inverse function. Okay, questions? No, okay.
Wait,
So
I have a question.
yeah,
doesn't the first example not pass the horizontal line test?
Exactly. That's why I kept saying, we're not gonna call the green the inverse function. It's just an inverse relation,
Okay.
an inverse function. Yeah. So it has an inverse, but it's not an inverse function. Okay. All right. So these ones here
Wait,
basically.
do you mean the blue? You said the green. Wouldn't the green actually pass the horizontal line test? The blue wouldn't pass the horizontal.
Okay. So the blue is Y. Okay. The blue does not pass the horizontal line test. The green is the inverse. So what we're saying is, if the blue does not pass the horizontal line test, then its inverse, which is the green, will not be a function.
Oh, okay, got it.
Yeah. So these ones here, it says graph each function using a graphing calculator and apply the horizontal line test to determine whether the inverse function exists. There is really very little you have to do for this one. You just have to graph and then, see, just visually inspect. So for this one, it's just, what is it, 4x squared plus 4x plus 1. Okay, all you have to do is look at it. Clearly, it does not pass the horizontal line test. Then, and you say, no, it does not have an inverse function. Okay. When you graph this one, it's going to look like this. That does have an inverse function. That's all. Okay. Now, if the function passes the horizontal line test, so now we've got a cute little function that passed the horizontal line test. We say it's 1-to-1 because no x value has more than one y value. So for example, look at this. This is something that passes the horizontal line test. Why is this 1-to-1? Because for each x value, I get exactly one y value, correct? Yeah. Also, for each y value, I get only one x value. That's what it means to be 1-to-1. Okay, now look. Don't dwell on this part too much, okay? Just know that this concept exists. What I need you to understand, what is important moving forward to next year is this. Remember how in here we said in going from a relation to its inverse, the x and y coordinates are switched, right? So now, in this function, in this relation here on the left-hand side, what's the domain? This represents the domain, and this represents the range, right? Well, what happened when we switched over to the inverse? The domain and range swapped. That's the consequence of switching our x and y values. So that's what I need you to understand. In going from one function to its inverse, the domain of f will become the range of f inverse and vice versa. Okay, so for example, suppose you have y equals, oh, I don't know, x minus 2. Okay, now you might just be given a function like that, and right off the bat you might be asked, what is the domain and range of y inverse? Not y, but y inverse. So for that, here's what you have to do. What's the domain and range of this? This is root x minus 2. So it starts from 2 and it goes up, right? So the domain is to infinity. And what's the range? 0 to infinity. Are you guys okay with this, or should I go into why? So now the question, though, that's not what it's asking. The question is asking what's the domain and range of y inverse? So you would switch them and say the domain of y inverse is 0 to infinity, and the range is 2 to infinity. Okay? All right. So let's see how we find inverse functions. You've done all this in algebra 2. So first, it says to determine whether it has an inverse function. And what you can do is you can graph and check to see if it has an inverse. Okay, this one does. Okay, so here's what we do. We rewrite it as y equals the function. Then we switch x and y. Right, so this becomes x equals y over 2y minus 1. Then you solve for y. So I'm going to cross multiply here. 2xy minus x is equal to y. Bring all the y's to the same side. 2xy minus y is equal to x. Factor out a y. And then y is 1 over 2x minus, I'm sorry, what happened here? X. This was x, sorry. Y equals x over 2x minus 1. Okay, that's the inverse. So I have to label it as inverse, right? I say f inverse of x is x over 2x minus 1. Oh my God, what happened here? The inverse of this function is the same thing as the original, so it's its own inverse. Does that happen? Is that okay? It's okay. Okay? All right, go ahead and do the next one. Okay? Find the inverse for me, please.
Was this one just a coincidence that it was the same thing?
Yeah, it was the coincidence. That's why I like this, because we don't want to get thrown off by these things. All right, I'm gonna pause the recording while you guys do this. Let's see. Is this what you guys got? All right, we do have a problem here because take a look. This, right, f of x is 2 root x minus 1, which is this. Okay, I'm sorry, it's this. Okay, it's just that square root graph. But look, f inverse, right? What we got for f inverse, that's a parabola that looks like this. Is that green the inverse of the blue? It's not, right? What's different? The blue only has one side, whereas the green has two. So what would be the correct inverse? It would just be that part of it, correct? So what we have to do now is we have to restrict the domain of our inverse so that it represents the correct portion of the graph. So I say the inverse function is this with a domain of 0 to infinity. Okay, in order to match the correct portion of the graph. Yeah, Evan?
So do we just kind of manipulate it there to show what we want it to show? Like, are we allowed to just kind of forget about the left side?
Yes, not only are you allowed, you're required to. Because for the inverses, you have to work within the correct domain. Jonah?
Is there ever a time where they don't have an inverse function on one of these? Because it says like determine whether each function. Is there a time where like there's not?
It might be on actually the next one. The next one is an interesting case. So if you're given one and you graph it and you're like, okay, this does not have an inverse function, you don't even attempt to find it, right? So take a look at this next one, actually. What you're given is m of x is equal to x squared. Now, on its own, right, this would not have an inverse function because it's a parabola and it does not pass the horizontal line test. So we would have said, you know what, no, can't find an inverse function, sorry. However, look at what we're given. In addition to this, we're given a restricted domain. This says the domain is only from 0 to infinity. That means, right, that if this was the parabola, when it says the domain is only from 0 to infinity, it's only that part of the parabola. And that does have an inverse function. Okay, so when I find it, y equals x squared, switch x and y's, take a square root of both sides. What do I get here? Y is equal to plus or minus root x. But again, what does plus or minus root x look like? I've got a top part and a bottom part. But look, the inverse of this is only one of those arms. So I can't take the bottom part. That means m inverse of x is only positive root x. All right. So now, suppose you're given two functions and you're told, okay, these are inverses of each other and you have to verify them. So you know how in the beginning we said a function and its inverse is a reflection around the x-axis, around y equals x? The theorem says this. If two functions are inverses, if and only if you do f of g of x, you get x. And if you do g of f of x, you get x. Did you guys do this in algebra 2? Do you remember? We don't know. It's okay if you didn't. So the question says to verify that f and g are inverses of each other. Okay, so now here's what you have to do. Split your page into two. In this first part of the page, you have to find f of g of x. And in the second part of the page, you have to find g of f of x. So let's just do that. F of g of x is inside of f of x, I'm going to put g of x. Okay, this is like magical. Okay, check out what happens. Inside there, I get x squared minus 10x plus 25 plus 5. Okay, check out the magical action here. This factor x minus 5, x minus 5, which is x minus 5 squared plus 5. But what's the square root of x minus 5 squared? Is it just x minus 5? Oh my God, it is. Plus 5. What do we get? X. How fantastic is that? Right, we're halfway there. We did f of g of x and we got x. So now let's do g of f of x. There's no way that's going to give you an x, right? Well, let's see. There's a little bit of math here. So we're going to put f into g. So it's going to be x minus 8 plus 5 squared minus 10 x minus 8 plus 5 plus 33. Okay. Okay, so what happens here? Look, in this first parenthesis, I square the first one, I get x minus 8 plus 2 times 5, 10 times the root, 10x minus 8, 10 root x minus 8, plus square the last term, you get 25. Okay, next, distribute the minus 10, minus 10 root x minus 8, minus 50, plus 33. Okay? All right, guys, what happens here? 10 root x minus 8 minus 10 root x minus 8 cancels. What do I have left here? Minus 8 minus 50 plus 25 plus 33. What happens there? That's minus 58 plus 58. All goes away. What am I left with? X. Isn't that cool? So look at what happened. F of g of x and g of f of x both gave you an x. So you say, yes, they're inverses. Okay, so somebody's now thinking, oh my God, Miss Malikian, like seriously, you know what I could have done? I could have just taken f of x, find the inverse, shown that it's g of x, and boom. Okay, but you haven't verified. To verify mathematically, you've got to do it using the theorem. Okay? All right, last but not least, you need to be able to graph an inverse using the graph of the function. Okay, and this is very straightforward. What you do is you pick coordinate points and then you have to flip them. Okay, so what are some points here? I got -3, 0. I have 1, -2. What's another one I have? 6, -3. For the inverse, you switch them. Okay. And then that's what I'm going to graph. So 0, -3. X is 0, y is -3. X is -2, y is 1. X is -3, y is 6. Oh, that's what that looks like. Okay, so that's the inverse of the graph. Look, if I fold over that red line, does the blue match up with the red? It actually does, right? You can cut this out and you can like fold it, and I promise you that's what it will be. Right? So look at this next one. What are some points we can take here? I got 1, 0. What's another one I have? Do I have any quarter points? corner points, I mean, I don't really. So like this one is, roughly 2.5 comma 1, right? But look at some other important characteristics I have. It looks like there is a vertical. When I said vertical, my first grader just said asymptote. They're learning. It looks like there's
You're
a,
ready for algebra 2 and pre-calculus.
it looks like there's a vertical asymptote at x equals 0, right? So now look at what's going to happen. This first point is going to switch to 0 and 1. This is going to switch to 1 and comma 0.5. And the vertical asymptote will switch to a horizontal asymptote, y equals 0. Okay, everything switches like that. So I have a point at 0 comma 1. And then I have one at 1, 2.5, roughly. And then it looks like I might have a, like a horizontal asymptote here, right? In the negatives, right? Vertical asymptote is in the negatives, and so is the horizontal asymptote. So it kind of, will go up like this. Again, look at how it's mirrored along that, like how it's reflected around that red line. Okay? All right. So that's that. So, we're just focusing on, X and Y being switched, domains being switched, and so on. Sometimes a question might ask you, going back to this, if you have Y equals X squared, what should the domain be in order for you to get an inverse function? Okay? All right. So I'll stop here.